This is the third video in the exam review, and just picking up where we left off. Problem number 4, we have a symbolic derivative. G of x is defined to be a function of f of x squared plus 1, and in letter A they asked us to find the derivative of g. So if we're going to find the derivative of g, notice that g again is defined as f of, so there's an outside function and an inside function. So when we do letter A, we're going to apply the chain rule, so we'll have the derivative of the outside, which is f prime, leave the inside alone. Then the chain rule says multiply by the derivative of the inside, which in this case would just be 2x. So if you want to rewrite it, I don't necessarily see a reason to. If it were a multiple choice question, it might be rewritten. But I could put the 2x in front as an indicated multiplication. In letter B, they're asking me to find the derivative at 2. Well, in letter A, I already found the derivative. So now all I need to do is substitute the number 2 in place of x into my derivative that I already found in A. So there's 2 times 2 multiplied by the derivative at 2 squared plus 1, which is 4 times f prime of 2 squared is 4 plus 1 is 5. And there's nothing else that I can do with that because I don't know the actual function for f. Letter C says find the derivative evaluated at x cubed. Well, again, I already found the derivative of g, so I'm going to evaluate it at x cubed. So I have 2 times x cubed. I'm just putting x cubed in place of the x. Derivative evaluated at x cubed. I'm putting that in place of the x squared plus 1, which is equal to 2x cubed times the derivative of f at x to the 6. Remember, when you have a power to a power, you multiply those powers. So that would be my answer for letter C. In letter D, they're asking me to find the derivative, and be very careful because these two are not the same thing. In letter C, it's an order of operations issue. In letter C, it says find the derivative first and then put in x cubed. Letter D says put x cubed into g and then find the derivative. So it's an order of operations. So step number 1 is to find g of x cubed. So I'm going to take the original function of g and put x cubed in place. So I take out the x, put x cubed in place. And so g of x cubed is f of x to the 6th power plus 1. Again, power to a power, you multiply. Step number 2 is so now I have g of x cubed. Now my job is to find the derivative of g of x cubed. So I'm finding the derivative of this function. Outside, the derivative of the outside function f is f prime. Leave the inside alone. Multiplied by the derivative of the inside, which is 6x to the 5th. And if you wanted to rewrite that, you could put the 6x to the 5th in front of that. All right, let's see what we have on the next problem. We have a given function. Use the graph of f to determine each of the following. So A, we want to know where is f continuous. Well, let's start with where is f not continuous. F is not continuous at this hole right here. Remember, continuity has to do with a break, gap, or hole. So f is continuous everywhere except -1. So I would say f is continuous from negative infinity to -1 open because there's no continuity there, and then from -1 to positive infinity. Now, some of you, if you want to put a u between that for union, you're welcome to do that. Either is acceptable. Letter B is a different idea, differentiability. Where does the function have a derivative? Well, again, let's go back. Where does the function not have a derivative? Well, clearly, since there's no y value here, you can't have a derivative where there's no y value. There's nothing on the function. We also know that we can't find the derivative at a sharp turn, which is here and here, or a cusp, which we don't particularly have in this scenario, but there are 2 sharp turns. Now, over here, you may be wondering, I would not consider this to be a sharp turn. I don't think they're trying to confuse us with that. But that's not a really sharp turn. It's curved. So the derivative exists from both sides. So so we're looking for the positive. Where does the function have a derivative? Well, there is a derivative from negative infinity all the way up to negative 1. No derivative at negative 1. Then we continue with the derivative. Oh, I missed a sharp turn right there. I almost missed it. So from negative 1 to 0, because at 0, that's a sharp turn. Basically, if two segments are coming together, you can consider that as a sharp turn. From 0 to 2, because there's a sharp turn at 2. And then from, what is this? 1, 2, 3. From 2 to 3, because there's a sharp turn at 3. These numbers are a little bit off. And then from 3 to infinity. And again, this answer says where the function is differentiable. So I left out negative 1, I left out 0, I left out 2, and I left out 3, because those are where I either had a discontinuity or a sharp turn. Problem number 6, this is one of our classic problems. We've done this problem a million times. We are trying to force this piecewise function to be continuous. So in other words, we need to make sure, because for a piecewise function, this value of 2 is the value that we're concerned about. We know that a parabola all by itself is continuous everywhere. We know that a line is all by itself continuous everywhere. So the only value we're concerned about is 2. Now, for the function to be continuous, we want to make sure that they have the same y value. So I'm going to substitute 2 in place of x. 2 squared is 4. 4 minus 3 is 1. Now, that's an open circle if I were graphing it, because it's not equal to. Now I'm going to do the same thing here. I'm going to substitute 2 in place of x, and 2 times a would be 2a. That's a closed circle. Now, in order to make this function be continuous, I need for this solid to fill up the hole, which means that they have to have the same y value. So 2a must equal 1. Therefore, in order for this function to be continuous, a must be equal to 1. Okay, in letter B. If I remember correctly, this problem always causes a little bit of dilemma. Let's see what's going to happen here, because it seems like there's something that doesn't agree, but we'll find out. Now look at your words. Differentiability, that should be in our minds telling us we need to find a derivative. And yes, you can find the derivative of a piecewise function. You find the derivative of each piece. So for the first piece of the function, the derivative of x squared minus 3 is 2x. And that's still defined for x is less than 2. And the derivative of the second piece, the derivative of ax, is just a. And that's still defined for x is greater than or equal to 2. Now, we want the derivatives to be the same in order to make sure that the function is differentiable. So I'm going to substitute 2 in place of x. So when x is 2, the y is 4. And there's no value of x to substitute 2 into, so when x is 2, y is a. So that tells us in order for this function to be differentiable, a has to equal to 4. So what we notice is that these two values of a are not the same. So we really can't make this function be continuous at x equal to 2 and differentiable at x equal to 2 at the same time, because it takes two different values of a. And now I'm not sure if they're wanting to us to consider this problem completely differently, or look at the whole thing and say, well, this can't happen, but it can happen. But that's the process. The process is correct, and that's how you would do the problem. Number 7, suppose that f is continuous on -5 to 5. So the first thing, when I look at this problem, I'm thinking I need to see a picture. And so the graph starts at -5, and the graph stops at 5. F of 0 is 2. So when x is 0, y is 2. I'm going to plot a point there. F of 3 is -2. So 1, 2, 3, 4. F of 3 is -2. 1, 2. the second derivative is positive from -5 to 0. So I'm going to make a little number line and put my information on there. Second derivative of x, they tell us that it's breaking from -5 to 0, so I'm going to put a 0 on here. We already know the graph starts at -5 and stops at +5. And at 1.5, I'm going to put a value there. So the second derivative is positive from -5 to 0 and from 1.5 to 5. So I'm concave up, concave up. F is decreasing. The original function is decreasing. Now that's going to help me a little bit with the first derivative. Decreasing to the left of 3 and increasing to the right of 3. So if f is decreasing to the left of 3 and to the right of 3, now we know the first derivative is negative and positive on that particular interval. Sketch a possible graph of f. Now I am assuming, I'm guessing that we're going to assume that the second derivative is negative in this interval since they didn't say that it's positive anywhere else. So we have a point of inflection at 0 and a point of inflection at 1.5, and we have a local minimum at x equal to 3. All right, let's see if I can make that happen. All right, so we're decreasing all the way to -3, decreasing with a point of inflection at 0. So decreasing, point of inflection at 0. All right, so I'm decreasing. I've got my little kind of cubic or S shape. I'm going to change the concavity to concave down. There's my point of inflection. Now my other point of inflection is at 1.5. This is going to be tricky. So my other point of inflection is here. My graph's kind of small. I'm concave down. I'm supposed to go concave back up. Now this graph would be a lot easier to draw if I had spread my axis or spread my values out. Now this is not a beautiful graph, but it does kind of, I would really work on this little region in here. I have concave up, I have concave down, and I kind of fudged it a little bit to go back concave up here. In class I will draw a better graph and do a little bit better job, but hopefully you can kind of see what's going on there. Again, what I would have done to make this graph easier for myself is to spread this my axis out, spread my numbers out so I had more room to make those points of inflection. Let's see if I have time to do one more. Actually, I think I'm going to save this for the next video.